Okay, so next thing we're going to do is just start solving some conduction problems. And again, we're going to use Fourier's law to do this. Now we kind of know where it comes from. In general, these conduction problems can be pretty complicated. So if you look up here, if you think about it, in a given hunk of material, you could have temperature that varies in all three spatial dimensions and then also in time if it's a transient problem, right? So that's going to be a very difficult problem to solve. And we're going to do sort of the typical thing, which is start simple and then get more and more complicated. So the simplest place to start here is one where the temperature is only a function of one dimension and not of time, right? So one-dimensional steady-state problems. So what that means then is that temperature only varies in one spatial direction, maybe x, y, or z, and we don't have a transient problem. We have a steady-state problem, so the temperature everywhere is not changing in time, right? So we would have temperatures only a function of x, where actually in this problem, temperature is only going to be a function of r, the radial direction. So this is the problem we're going to start with. It's a simple problem. It is a one-dimensional steady-state problem. It's a hollow cylinder, right? So this cylinder has got an inner radius of r in, it's got an outer radius of r out, and a length of L. That's the geometry, right? We've kind of cut it away so we can look at it. The boundary conditions are that this inner surface here is held at some uniform hot temperature, and this outer surface here is held at some uniform cold temperature. And then the top and the bottom surfaces are adiabatic. And so by virtue of those boundary conditions, the temperature is only varying in the r direction, right? Because energy is only going to want to flow from this hot surface to this cold surface, right? And it's not going to want to flow through these adiabatic surfaces. And so if energy is only flowing in the radial direction, then the only direction the temperature is going to vary is also in the radial direction. So this is a one-dimensional steady-state problem. Okay, so a nice place to start. We can solve this problem a couple different ways. In this class, we'll solve these kind of problems numerically, and we'll also solve them analytically, right? So an analytical solution is one where you derive a differential equation that governs the physics, and then you solve that differential equation in order to get a function. And the function satisfies the differential equation, and then it also has to satisfy some boundary conditions. So that's an analytical solution. A numerical solution is a very different thing, where you're not actually solving a differential equation. You're actually solving a bunch of algebraic equations. So let's do this one analytically. And the first step in getting an analytical solution is going to be to actually understand what the differential equation is that you're trying to solve, right? So we have to derive the differential equation. And you'll do this throughout this class and actually throughout your career. So it's pretty important, I think, that you can derive the differential equation that is appropriate for your problem, right? It's almost as important that you can do that as it is that you can solve it, because it does you no good to be able to solve an equation that is the wrong equation. So first thing we need to do is practice and establish some steps in terms of how we derive the differential equation. The steps are basically always the same. They get a little more complicated as the problems get more complicated, but the steps are the same. First thing you're going to do is define a differential control volume. So a differential control volume needs a little bit of discussion. So this is going to be differentially small in the direction that the temperature is changing, right? But it doesn't have to be differential in directions where the temperature is not changing. And the way to think about this is your control volume needs to include material that's basically all at the same temperature. So for this particular problem, my differential control volume would be differential in the radial direction because the temperature is changing in this radial direction. But it does not have to be differential in the axial direction because the temperature is not changing in the axial direction, and it actually also doesn't have to be differential in the circumferential direction, right? This is going to be what we often refer to as a shell, right? It's a shell. Imagine like a toilet paper roll where the thickness of the roll is taken to be as small as possible. So this is differential in its thickness, but it's not in x or theta. So there's my control volume. We are going to take the limit of this control volume going to 0. That's what's actually going to eventually give us a differential equation. We're going to use that idea to introduce some derivatives, right? But for now, this is our control volume. Step 2 is, now that we have a control volume, do the first law of thermodynamics, right? The first law of thermodynamics says that energy going in has to equal energy going out plus energy stored. And I can do that balance on any control volume that I choose to define. I just defined a control volume. It's right here. So my energy balance says whatever goes in, which is going to be conduction through this surface, has to be equal to whatever leaves, which is conduction through this surface, and whatever is stored inside of this control volume, which is 0 for us because it's a steady state problem. Right? Whatever energy I have inside of here is not changing, so the stored term is equal to 0. So for this particular problem, the only way energy can get in is through this heat transfer. The only way energy can get out is through this heat transfer. So those are the only two flows of energy on my control volume, and then my stored is 0. So it's a simple energy balance. It says Q dot in the radial direction at location R, that's what this is, has to be equal to Q dot in the radial direction at location R plus dr. That's what this term right here is. Okay, so that's step 2. The next thing you're going to do is take the limit as dr approaches 0, right? So you're gonna now take the limit as you make that control volume differentially small. You turn it into a shell. Okay, so here's our equation, our energy balance up here. That hasn't changed, right? But what I'm going to do now is allow dr to approach 0. And so we have to, again, remember our calculus. The definition of a derivative, dq dot in the radial direction dr, is the limit as dr goes to 0 of q dot in the radial direction at r plus dr minus q dot in the radial direction at r divided by dr, right? So if I'm taking the limit as dr goes to 0, this equation right here, which should be familiar to you from calculus, should tell you then that q dot at r plus dr is equal to q dot at r plus dq dot dr times dr, right? So that's this equation right here. And normally we don't go through this in such explicit detail, right? If you do this a couple times, you realize that when you take the limit as dr goes to 0, you're really just saying that, okay, q dot at r plus dr is q dot at r plus dq dot dr times dr. Right? And you sort of get used to doing that pretty quickly. But that's the step, and that's really what you're doing. You can't write this equation unless you've mentally taken the limit as the thickness of that shell goes to 0. So now that I have this, I can introduce this equation into my energy balance. Right? So this equation is the right-hand side here. So I have q dot r is equal to q dot r plus dq dot r dr times dr. If I cancel out these q dot r's, I'm not sure what this is. This is a mistake. But if I cancel out these q dot r's, I get this equation right here, which is dq dot in the radial direction dr is equal to 0. And this is the outcome of step 3 every single time. You're going to end up with a statement about energy, right? Your differential equation is fundamentally a differential equation that is enforcing the first law of thermodynamics, and therefore it will be a statement about energy. And this is a really good time to stop and step back and make sure it makes some kind of sense. So what is this saying physically? This differential equation is saying that the rate of change of conduction in the radial direction with respect to r is equal to 0. Right? It's saying in words that the rate of conduction in the radial direction doesn't change as I move in the radial direction. It must be constant, right? And if I go back and look at what we're doing here, that makes a lot of sense, right? If I have some rate of conduction at some radial location here, there's nothing adding or subtracting from that conduction. I'm not adding any convection, I'm not storing any energy, so therefore, no matter where I am in this material, q dot r has to be the same. And that's all this is saying, right? This is just saying q dot r, the radial conduction rate, has to be the same everywhere. right? It makes a lot of sense. So this is a differential equation written in terms of energy. I've checked it. It seems like it's right. I want a differential equation written in terms of temperature. So the way I go from energy to temperature is with a rate equation. So that's the linkage between those two quantities. The rate equation for conduction is Fourier's law, right? So I have to substitute Fourier's law, which is right here, into this differential equation. So Fourier's law says that the heat flux in the radial direction is minus k times the temperature gradient in that direction, dTdr. I want the heat transfer rate, that's what Q dot R is here, so I have to multiply this by an area. The area is the area for conduction in the radial direction, right? So if I'm conducting energy in the radial direction, the area that I have is the area of this face right here. So that would be 2 pi r times L, right? That's the surface area of this face. It changes, right, as I move from the inside to the outside. So I multiply this by 2 pi r times L, and then I substitute this whole thing into here, and I get this equation right here. I'm going to divide through by everything that's constant. So we're going to assume the conductivity is constant, 2 pi, and then L is constant, right? So I end up with this differential equation right here. This is my differential equation for temperature, right? And we see exactly the steps that we needed to go through to get it. I can solve this one pretty easily. This is a second order linear differential equation. What makes it easy to solve is it's separable, right? So I can take this dr right here and I can bring it up over here to the other side. So I can integrate both sides of this equation. If I integrate the left side, I'm integrating an exact differential. So the integral of d of r times dTdr is just r times dTdr. If I integrate the right side, I just get 0 because the integral is 0 is 0. And then it's an indefinite integral, so I have to have a constant of integration somewhere. I'm going to put it over here on the right side. I'm left with another differential equation. This one is first order instead of second order, but it's also separable, right? So I bring the dr and the r over to the right side, and again I integrate both sides. The integral of dt is just t. The integral of dr over r is the natural log of r, and one more constant of integration. And here's my solution, right? This is a general solution to the differential equation. This solution right here will solve this differential equation right here, no matter what value of C1 and C2 that I put into here, right? So these are the constants of integration. Of course, I have to have a certain C1 and C2 for my problem. And the way that I pick C1 and C2 is if I go back here, I have to make this function that I just derived satisfy the boundary conditions at the two edges of my computational domain. So my computational domain goes from R in to R out. At R in, there's something that my function has to do. It has to be equal to TH. At R out, there's something else that my function has to do. It has to be equal to TC. And so in order to enforce those two boundary conditions, I get C1 and C2, and that's what I've done here. T at R equal Rn is TH, T at R equal R out is TC. So if I plug my general solution into this equation and this equation, here I get two equations in these two unknown constants, and we can solve them, and we've solved the problem. All right, so that's where I want to stop today. What I'd like to do tomorrow or next lecture is think a little bit about how we can use Maple to help us do these kind of math problems. So this one is a problem that I really didn't need Maple's help with. Right, I'm smart enough to do this one all by myself. But you're going to find that Maple is still a pretty handy tool as the math gets more and more difficult. And Maple is symbolic software that basically, among other things, can solve differential equations and algebraic equations for you, right? So, I kind of use it as a really, really sophisticated math textbook that remembers things that I've forgotten, right? And it's really good at solving these kind of problems. There's a Maple tutorial in Appendix A2 of your book. I'll link that to the course website so that you can see that if you want. And then Maple, of course, is available through CAE, so you can use the you can use the Maple software if you're a UW student. Next time we'll walk through some of the very basic commands that you need to use Maple, right? And we're going to use like 1% of the software in this class, but it's still going to be pretty useful, right? So, even if you don't really know what you're doing in Maple, I think you'll be able to learn what you need to know for this class pretty quickly, and that's where we'll start next time.